Good morning, guys. Today we're going to look at multidimensional arrays. The sort of biggest piece of this is going to be the sort of cellular automata idea. That's how I'm going to sort of illustrate these sort of two-dimensional arrays. But I'll give you some general information about sort of what it means to create a multidimensional array and sort of how you can visualize it as well. We'll do a little bit of programming. We're actually going to program up a 1D version just to print out to the console for a specific cellular automata, and then we'll talk about a 2D version, and I'll show you some runs of the 2D version as well and sort of talk a little bit about it. So essentially, a multidimensional array is just an array of arrays. So we've talked about array elements being sort of single things like a number. So we have an array, it could be full of ints, for example. But most languages allow you to make each element another array itself. So an example of that would be a matrix. You've probably dealt with matrices before in math class. You'll have more of that when you take like a linear algebra class. Essentially, I'm saying that each row, rather than just being one single number, like in a regular sort of one-dimensional array, each row is an array itself. So here we have 3 rows. Each row has 2 elements. So I can create an array like this. This is one of the ways to create a regular array by specifying the elements, but we can make it so that each element is an array itself. So that's why we get the 1, 2 as the first row, 3, 4, and then 5, 6. And then accessing this array is the same as we've done before, just another set of brackets. So we're accessing element 2, which is, we write out the elements. We have element 0, element 1, element 2. So we're accessing element 2, which is this one, and we're accessing the 0th element of that array. So this value would be a 5. And it's the same sort of thing you would do if you did row, column. We are in row 2, column 0. If we counted this as 0, 1, and 2, and then 0, 1. Row 2, column 5. So accessing these arrays is the same as you would sort of think about in math class, sort of a row column format. And creating these arrays can be done in sort of a very sort of easy way, a very sort of standard way of just each element being another set of brackets to create an array for that element. There are other ways to create them as well. The generic form, just to create an empty two-dimensional array, would look something like this. So in this case, I'm saying we have a 2D array, so I do need the 2 sets of brackets after the type. And then I'm saying there are 3 rows and 2 columns. So this is rows, and this is columns. So 3 rows, 2 columns for this particular array. So this creates one that has all zeros. Just like if we created a 1D array, it would be all zeros as soon as we do this. This does the same thing, except it's a matrix in this case. Sort of visually, it's a matrix, 3 rows, 2 columns. There are other ways to set this up and to sort of fill the values. So we just saw this way. So this is if you already know what the value should be, and it's relatively small, so you don't need like a loop or something. Then you could just fill them in. Another way to do the same thing, this might look a little bit weird, but another way to do the same thing is this. I can say, all right, I'm going to have 3 rows, but I'm going to have an unknown number of columns. And then I can say the first row is an array with a 1 and a 2. So this is another way to do it. This is another way to create potentially a different number of columns for each row. I don't have to have 2 columns in each one of these rows if I don't want to. I could make what's known as it depends on sort of what professors you have for math and stuff, but I would sort of call this like a jagged matrix or something where you don't have the same number of rows or same number of columns in each row, for example. So you can do something like that. That's a relatively, to me, it's sort of a kind of a natural way to think of it. Say that I want a 2D array, 3 rows, but I can set the columns up any way that I want to. So column 0 has a 1 and a 2. Column 1 has a 3 and a 4, and so on. Another way to do it is to just create that empty full matrix. So 3 rows, 2 columns. And then I can just go through and fill each individual element. So for 0, 0, I want a 1. So row 0, column 0. Row 0, column 1 is a 2. And all of these will make the exact same matrix. 1, 2, 3, 4, 5, 6. They will all make the exact same one. They're just different ways of messing around with those 2 indices and how you can create columns and how you can create rows in your matrix. In CS2, there's actually one of the homework assignments is a matrix multiplication. So you will be dealing with 2-dimensional arrays much more in the future. They can be quite handy, not just for the math aspects, but also for a representation. Say you are you want to program a game that's kind of like, I don't know, something like Civilization, where you have like some sort of grid. So either square grid or hex grid or something. Having a 2D matrix represent that grid is a very natural way to do that. So it's a sort of this idea of representing data in a 2D format like this is all over computer science. And that's something that we're going to look into today. First, we'll do a 1D version to hopefully sort of get the concept of this down. And then we'll look at a 2D version that we're not going to program up because it does use some extra graphic stuff. But typically in a CS2 class, we do code up the 2D version that you're going to see today. So that's the basics of sort of 2D array stuff. You're not going to have any homeworks where you have to do 2D array stuff this semester, but it will become more and more sort of useful for solving problems and doing homeworks and projects and stuff as you move through CS2 and potentially other computer science classes. So today, the main thing to sort of show this stuff off and to show a little bit more with sort of regular 1D arrays as well is this concept of cellular automata. And some of you may have seen this before. There's a very common application of this that's usually shown in sort of intro programming classes. So as an example of 1D arrays, 2D arrays, I'm going to talk about how we can take these array values and actually have them represent something more visually, which I think can be more useful than just seeing a bunch of numbers and kind of like what we did last time, see a bunch of numbers and find the largest one, for example, or see an array of numbers and make a copy of the array or something like that. Those things are useful, but they're not very visual. They're not very exciting. So today is the sort of hopefully more exciting piece of what you can do with arrays, because it is a bit more visual. The video game Noida had its, I think it has 1.0 release here in the past week or so. It's been in early access for a little while. If you read sort of the description of this game, they talk about how every pixel is simulated. Those material simulations, those material and sort of gas and fluid and solid simulations, the interactions that you see in that game are entirely based on this concept. I wrote a paper with a student where we went through and we sort of used some of the Noida ideas as a base and went through and made a probabilistic simulation for some of the sand motion that you see in Noida. It's different than Noida's version, but it's sort of a similar style to their sand simulation, but using some probabilistic stuff. So if you play this game, great, you sort of know what I'm talking about. If not, if you even just go take a look at a trailer, you'll see all of these interactions with gases and liquids and solids, and you'll sort of see how they interact with each other, and they sort of look like the pixels are sort of moving around and sort of doing sort of what you would expect them to do in sort of a realistic situation. That is all based on this concept that we're going to talk about today. You would have to go further with it to make a game out of what we're going to talk about today, but the basic idea is what's coming up. So hopefully this is a little bit of a motivation to think about this stuff maybe a little bit more. All right, so the best known example of a cellular automata is Conway's Game of Life. this isn't the game of life where you have the little sort of spin thing and then you get married and have kids and go around the board and stuff. It's not that game of life. Most likely, I wouldn't be surprised if a lot of you have seen this before, but maybe not sort of remembered what it's called. It's a cellular automata simulation from the 1970s, and it's a zero-player game. So it's not really something you'll interact with. It's just entirely determined by the initial configuration of the play area. So essentially what you have is a full board of a whole bunch of squares. And some of those squares are like in the on state. So they might be like a black square or something. And some of them are in the off state. So they might be white. Based on the configuration, every single time you update the board to a new configuration, it's based on the previous one. So you can sort of think of it happening over time. So you start in some initial state, and the next sort of time step, it moves to a new state based on that previous one. So we're going to look at those rules, sort of how you do this update. What does this update mean? But first, we're going to start with a 1D version, and we're actually going to code it up. And then we'll look at the sort of a 2D version. So your question might be then, well, okay, what is a cellular automation? What is a cellular automata thing? So it's just a system of cell objects. So it's just a bunch of cells. And they might be squares, they might be hexagons, they can be whatever shape you want. But they always have the following characteristics. They always live on a grid. We'll look at 1D grid and 2D grid today. But you could have a 3D grid very easily. You could have a higher dimensional grid if you want to, a 4D grid, 5D grid, whatever. The math all works out. Of course, displaying a 4D grid and sort of visualizing it, probably going to be a little bit more difficult than 1, 2, or 3D. But you can do it. The math all works out. You can have a 4D matrix and do all sorts of stuff that you want to with it. Each cell has a state. Usually this is a finite value, not always, but usually it is. So I mentioned sort of on or off, 0 or 1. That's the idea. That's the state. Finite state, only 2 possibilities in Conway's game of life, which represent like alive or dead. In our code, we'll represent it as just numbers. But for other types of simulations, like something in Noida, you might have a whole bunch of different states. And each state might have different properties. So like a certain fluid might have a density. And so then you get some interesting interactions when when certain fluids sort of interact with each other, they sort of mix or something. Each cell has a neighborhood. This is one of the key concepts as well. And you can define this in many ways based on the type of simulation you want to do. We'll look at one specific type in 1D and a different one in 2D today. So this idea of the cells you have cells on a grid, each cell has a state, and each cell has this thing called a neighborhood. So then what's a neighborhood? Well, if you pick any cell, so let's say I pick this cell. What's this cell's neighborhood? In game of life, it is all the adjacent cells, including the diagonals. So you include the cardinal directions and you include the diagonals. That's the neighborhood. So you can think of every cell, all 9 cells in here, so including that center cell, as sort of the full neighborhood. So I pick a cell, and this is a very common thing in cellular automata. I pick a cell and I change that cell, the value of that cell, based on the 9 cells that this square here, the outer square here, encompasses. That's the whole idea of a cellular automata right there. And that's sort of one sentence. Pick a cell, update that cell's value based on its neighborhood. For 2D, it's a little bit more complicated, right? We have 9 total cells here. For 1D, it's going to be a bit simpler, which is why we can program up the 1D version relatively easily. The 2D version takes a bit more time. It's a little bit larger of a project, especially when you add some graphic stuff to it. So all of this came about more or less in the 1940s at Los Alamos National Laboratory. This idea sort of came from Stanislaw Ulam and John von Neumann. Ulam was interested in crystal growth, and von Neumann was interested in self-replicating robots. So they were sort of working on ways to, how do you think about these self-replicating robots? How are they going to replicate over time? Or how are crystals going to grow over time? And if you sort of think about it a little bit, like something like crystal growth, it sort of makes sense. The growth of a crystal will build on crystal that's already there. So you have a little sort of starting point where the crystal starts, and then it'll sort of grow based on crystal that's already grown. So you can probably imagine how this could work with cells and changing the state of a cell based on what's around it. The most significant work, this was done by Stephen Wolfram. If you've used like Wolfram Alpha or Mathematica before, it is this guy, the same guy. He wrote a book in 2002 named A New Kind of Science, and it explored cellular automata in physics, biology, chemistry, basically a whole bunch of physical sciences is where he explored this. So things like fluids, things like growth of bacteria, things like chemical reactions, all kinds of stuff. So this idea of cellular automata isn't just to have fun with a little bit of computer science. It can be used in these sort of science concepts as well as sort of physical science concepts. So that's just a brief bit of sort of where this came from. All right, so I want to talk about a 1D version of cellular automata because we've messed around with arrays. Arrays are just 1D lists of numbers. So we can play with arrays and create a cellular automata based on one-dimensional arrays. So that's sort of the simplest CA that we can really have. Something where we have a 1D grid, we have two states, say a 0 and a 1, and a total of a 3-cell neighborhood. So it kind of look like this. We've got this little 1D array here. We don't have any values in there yet. We'll fill it with stuff in a second. We have a 1D array. We can make that in Java relatively easily. So we fill it with 0s and 1s. And then we do this concept of picking a cell. So I pick a cell. And then I look, what would I call my neighborhood here? We can choose whatever neighborhood we want. I'm going to do just a simple 3-cell neighborhood. So the cell that we've picked and the 2 directly adjacent. Simple neighborhood. So I would see that to the right is a 1, the center is a 1, or to the left is a 1, the center is a 1, and to the right is a 0. Easy enough. This neighborhood and state configuration and grid can actually give us something really cool. So as we sort of go through this and talk about how you do an update and sort of how this is done, you probably won't be able to tell what kind of sort of cool structure it will make. When we code it up, then you'll start to see sort of how this works. There are some questions to answer about this. What if, so I just picked one of these cells in the middle here, but what if I picked one on the edge? What if I pick this one? Well, there is no right neighbor here. Just like on the other side, there is no left neighbor. So if I drew the neighborhood, it would look just like this. We'd have the 0 to the left and the 1 in the center and then nothing to the right. So what about the edge? That's something we'll have to think about. Okay, so let's say you have a setup of 1s and 0s. So then the question is, now what? What do we do? Well, we want to update this array based on some set of rules that we come up with. And I'll give you the rules in a moment. Once we update it, we get the next sort of generation. Think of it as time. So we update, we get a new generation with potentially different values. And then we do it again. We take this generation 1 and we update it to generation 2. And so we're going to visualize this by sort of stacking these generations on top of each other. Think of each one as like a black square and each 0 as a white square. So I'll get some pattern of black and white squares as the generations go on. That's the pattern that actually comes out to be really cool that we're going to see once we code this up. All right, so let's do an update. Or let's think about an update. Let's think about the rules for this. So we have a description of the neighborhood. Let's figure out what the next generation is. The neighborhood in a cellular automata always determines what the next cell is. So I'm going to do some kind of calculation. I'm going to take this 1, this 0, and this 1, and I'm going to do a calculation. It might be as simple as an if statement. And then I'm going to update it to some new value at the same center one that I picked. So that's part of this as well. If I pick this cell as the center, this is the one that gets updated here. So no matter what calculation I do, let's just say, for instance, I add up all the values here. And that's what happens here. So 1 plus 0 plus 1, I get a 2. This would become a 2 because it was the cell I picked. Now, I've told you my CA that I've developed here is only 0 and 1 for the state. There is no 2 for the state. So I have to do some other kind of calculation to get this to work the way that I want it to. But that's the idea. I take the cell, I do the neighborhood, I do some calculation, and I put the value in the equivalent location of the center cell in the new generation, the generation 1 in this case. So that is one of the sort of the key aspects. Take the neighborhood, update the center cell in the next generation. So we need a set of rules. And we can come up with any rules we want. In fact, changing the rules slightly between sort of two different simulations can give you totally different results. As an example, the 2D simulation that we're going to do, that I'm going to show you, and that I usually do in CS2, changing the rules can actually give you a blur in Photoshop. If you've used Photoshop or GIMP or Affinity Photo or something before, and you've done like a box blur or a Gaussian blur before, that's a cellular automata. It's exactly the same thing, which I've always thought was really cool. All of these things, from a sort of a curiosity in computer science to image processing to doing fluid simulations in physics, can all be done using the same concept, just with a different set of rules and maybe a different neighborhood. I've always thought that was pretty cool. So for a 1D CA, we can actually look at all possible rules for those 3 values in our neighborhood. So ask yourself, how many rules are there for 3 1s and 0s? Essentially sort of a binary counting thing. There's just 8 total configurations. I could have all 0s. I could have a 0, 0, 1. So again, we have the center cell, the one to the left, the one to the right. That's what I'm meaning here by these values. So I could have 0 to the left, a 0 in the center, and a 0 to the right. That would be one possible configuration of 1s and 0s in my neighborhood. And then I could have all the rest of these as well. Make sense? I could code up stuff individually for all these, and we will. There's a better way to do it, but we'll code up all sort of individually from these. And then I can just say, if I have all 0s, that update gives me a 0 in that center cell. If I have a 0, 0, 1, it gives me a 1. If I have a 0, 1, 0, it gives me a 0, and so on. This is what's known as Rule 90. Rule 90 is what Stephen Wolfram named it, because you could do the binary of this set of values here, and it'll come out to be a decimal number of 90. So in Stephen Wolfram's book that I mentioned, he tried every single combination of rules. He did every combination for the 1D cellular automata and looked at what the result of every single one of those was. And that is actually all in his book. We're going to look at an interesting one that gives you something that's kind of cool. So I have picked these rules very specifically. So I'm going to do a quick handwritten example. Let's say we start with all 0s on the left, all 0s on the right, and a 1 in the middle. So if we start with the middle, then we have a 0, 1, 0. Remember what our rules look like, and you might have to go back to the previous slide. Our rule for 0, 1, 0. 0, 1, 0. Our rule was a 0. So this gives you a 0 in the center. So if I keep going on the slides, that's what we get. Then we move over. 1, 0, 0. If you look back at our rules, that gives us a 1. So we update that center 1. And we keep going. All 0s gives us a 0. All 0s gives us a 0. We're on the edge. I said we had to deal with that, huh? For now, essentially the way that we're going to handle this when we code it up is we're just going to assume that if we go sort of off the edge, it's just a 0. In reality, what that means is I'm just going to not go to the edge, but we're sort of assuming it's a 0, sort of a fixed value at 0. But there's a lot of other ways to handle it as well. So here I'm saying, okay, if I just say that the thing off to the right here is 0, then this would be a 0, 0, 0, and it would give me a 0 value. There's other ways to handle this. You could keep the edges constant, which is sort of how we're going to handle it when we code it up. It's sort of this, the edges will always be 0, so that's sort of how we're going to do it. You could do it so the edges wrap around, right? I could just say, okay, 0, 0 for this one to the right. Let's just go all the way to the other side and look at that one. In this case, it would still be a 0, so this would still work. So that is another way to do it. You could have the edges have different rules, different neighborhood. The neighborhood here is 2, sort of 2 technically. So I could just have a set of rules for the edges and have those be sort of consistent and sort of what I want for my simulation. So there are lots of options for how to handle the edges. We're going to take a very simple approach that you'll see when we code it up, so we don't have to sort of mess around with it too much. If we keep going, 0, 0, 1 in our rules gives us a 1. And then we have all zeros for the rest. So the second generation, based on the rule 90 that I showed you in the previous slide, and a start that has a 1 in the center and all zeros to the left and right, gives us this pattern. Doesn't look very interesting, most likely. But as we see more and more generations, you'll notice it starts to come up with a pattern. And some of you, especially, I don't remember if I have any applied math folks in here, but some of you may have seen the pattern before. You may even know the name of it. So that's something that we'll see here in just a few minutes. So we have the first generation. That's the first CA simulation that you may have ever done. Now, it's a little bit tedious. And you could keep going. You could keep handwriting this out. All you got to do is pick a center, 1, 0, 1. See what the rule says. 0, 1, 0. See what the rule says. 1, 0, 0. See what the rule says. You could do this by hand and write it all out. When John Conway first made Game of Life, the 2D version, they literally did that. To figure out what the rules needed to be, him and some of the people that were sort of doing research with him literally would do a few generations handwritten. This was back in the 70s, right? So he didn't have fast computers and access to computers all the time. So he would literally just do it by hand, which tells you that the rules are simple enough, even for the 2D version, that doing it by hand was possible, which is one of those other really cool things. All right, so I am going to sort of, if you were doing this visually, you would probably treat it as the sort of squares. Like I said, you'd have white squares and black squares, so you could visually see everything that was going on. So if all of your squares are black, then you would end up with a white square. If all of your squares were white, you'd end up with a white square. And then you have your various combinations in there. So like I said, this is rule 90. And on a computer, we are just going to do this in the console. So we are going to print out, at least initially, zeros and ones to the console. And we'll make a small modification of that. We're not going to have sort of black and white squares because, well, obviously in CS1 we don't talk about sort of graphic stuff. That's a CS2 thing. But we will do sort of graphics things in CS2 with Cellular Automata as sort of a larger project. So I want to flip over and code this now. So does anyone have questions about this 1D version so far? All right, so I think it's no. So I just have an empty Java project. I didn't put this one in the in-class one. I made a separate one for it. So I'm going to make a new class, and I'm just going to name this class capital M main, and make sure I'm going to include the public static void main. And open. There we go. All right. So the first thing I'm going to do is create my array. I need a 1D array of whatever size I choose. So I'm going to make this integers. We're going to have zeros and ones. And I'm just going to call this, I don't know, I'll just call it A. And this is a new int array of size. Let's make it, we should make it odd because we're going to put a 1 in the center and have the same number of zeros to the left and to the right. So I'm just going to call this, let's just say 11 for now. So we got a 1 in the center and we have 10 other values. So 5 on the left, 5 on the right. So I have an 11 element array, and let's take the midway point. So right now they're all zeros, right? We have an array full of zeros. Now let's take the halfway point. Well, that's just going to be element a.length divided by 2. And I'm just going to set that to be a 1. Hopefully this makes sense. Whatever the length of my array is, which in this case is 11. but we're going to change this later. We're going to increase the size. So I'm going to actually just put a.length here. So that's all. I could put in 5. That's the value that would come out of this. This is an integer division. So the value come out of this would be 5. I could hard code a 5 in there, but this way I can change the number here and not have to worry about the index here. So I'm making it a little bit more generic. So now we have an array full of zeros with a 1 in the center. Awesome. Let's write a quick method to print it out, because we're going to want to see it in the console. So just like we've been doing, just like we did last time, just like we've talked about over the past couple of weeks, we're going to make a quick method. So public static void is just going to do some printing. And I'm going to say print line, print a single line. Or I could call it like print gen or something, print a generation of my CA. So I think I'll call it print line. And this needs to take the array that we're going to print. So it uses some of that stuff that we talked about last time. It's going to take an integer array that I'm going to call array. Actually, I'll just call it A still, just so it's less typing overall. I want to print the full line, the full array on one line, and then do a new line so that the next time I print, it'll print on a brand new line. So as sort of our standard thing with arrays, if I want to do something to every element, I should use a for loop. So we'll say I equals 0, I less than a.length, I plus plus. And we can print out, so system out printf, I can print out an integer and a space. That's what I want to do. And I'll print out the value I print will be the I index of A. And then after the loop, because here I don't have any new lines, there's no new lines here. After the loop, I want to print a new line like this. So the next time I print, it will be on the next line. So in main, I can call this method. Print line, send in A. Send in my array A, I run it, and there it is. And if I do print line here twice, then I get 2 lines like this. Now I haven't changed the array at all, so obviously it's going to print the same thing twice. But that's the purpose of my print line. Print this out, put a space between each one, and then put a new line at the end so that the next print is on the next line. So that's the whole purpose of this here. So we'll leave the print line there. The next thing I want to do is apply those rules. So let's do that as well. Let's do a method. Let's write a method to apply the rules. Public static. We'll do void as well. The only thing I'm going to do here is change my array. I don't need to return any values back. There are other ways to write this where you might have a return value, but I'm just going to update A right here. So I'm going to say void. Let's call this update, or let's call this apply rules. And I'm going to send in, again, I'm going to send in my array. This time I'm actually going to call it array. You'll see why in just a second. I mean, in principle, you can call it whatever you want to, but I'm going to use A for something different in this apply rules method. Now I'm going to do something wrong first. I'm going to do this so it actually doesn't work first. But it's the way that you might do it if you've never coded a CA before. Because it's not something that you realize based on the slides that we talked about today. I need to check every neighborhood. I'll go back to the slides real quick. What's the neighborhood? It's something like this. So I need to pick a cell, pick an index, and look at the one to the left and look at the one to the right. And I'm going to leave the edges so that we never actually are on the edge. The cell that we pick, the cells that I pick from this picture are only ever going to be like this. Only ever going to be these cells. I'm never going to pick this one, and I'm never going to pick this one. They still exist because I need them for the neighborhood for example, when I pick this cell. But I'm only going to pick between, so we put the index here, 0, 1, 2, 3, 4, 5, 6, 7, 8 for the indices. I'm only going to ever choose an index between 1 and 7. Never 0, never 8. So for my loop, this is my loop to pick a cell, pick a center cell. So we'll do this. Typically we say for I equals 0, right? But I don't want 0. I don't want index 0. I don't want this first one. So I'm going to say I equals 1. That means I'm going to start with that cell. I'll pick that as the center cell. Then I'll say I less than. Well, normally I would say array.length. But I don't want to go all the way to the end. I want to go 1 less than the end. So what would I do? I'd say -1. And then I++. So here, this is never pick the left or right edge. Because I start at 1 and go to array length -1. Now we can grab the 3 cells we need. So I'm going to create another int here called A. I'll create one called B and C in a second. Let's say A is the cell to the left of the one I've picked. Well, the cell that I've picked is array I. That's the cell that I currently picked. I start with 1, so I pick this cell. Well, what's to the left? It's my current cell -1. If my cell is 1, the cell to the left of me is 0 for the index. So this to the left would be -1. Array -1. Array I -1. The center cell is just I. And the cell to the right is array I+1. So I+1 will give me the cell to the right of the cell that I just picked. So this one is here is to the left, center, and to the right. Is there any questions on this loop? All right, so once I've picked that, now I can apply my rules. So in the slides, let's go back up to where the rules were. These are the rules I'm talking about. So we have our values here. We have A, B, and C. So if A is 0, and B is 0, and C is 0, then our center cell becomes a 0. If A is 0, B is 0, and C is 1, then our cell becomes a 1. So that's why I've picked out A, B, and C, because I can use some if statements with it. If you sort of see how this is going to give you a long list of if statements, 8 of them to be exact, it will, and that's the way we're going to code it. The better way to do this is to use an array as a lookup table and stuff. But if that's something you want to ask a question about, we can talk about it afterwards or on office hours or something. So we're going to do it very simply right now. It's sort of the most naive way to do this is to use some if statements for our rules. So if we go back to the code, I'm going to say if A equals 0 and B equals 0 and C equals 0, then array I, that's my center one, equals 0. That's the first rule. Now we can do this for all of the rules. So I have 1, I need 8 total. So here is 2, 3, 4, 5, 6, 7, 8. Save that. Now they're all the same here. And I mentioned before, I mentioned probably a couple times that if you find yourself copying and pasting code, there's probably a better way to do it. And that is the case here. But again, I want to keep this sort of as straightforward as possible. So there's not a bunch of like lookup table things and using more arrays to store other things. And I don't want to worry about that. So we're just going to keep it like this. So now we need to look at, hey, what are all the possibilities? I'm not going to change the values for array yet, but I am going to change the stuff in the if. So we've got all zeros, and then we sort of count up in binary. So you can fill in all of these if you want to as well. And again, I'm just sort of counting up in the sort of the binary sense. So we go from 0 to 8 here for the sort of binary values. So a binary 111 is 8, and 110 is 111 will be 7, 110 will be 6, 101 is 5, and so on. So here we got 0, 1, 2, 3, if you count it up in binary for the A, what A, B, and C are. Now we got to look at what these array values need to be. So back to the slides, and I think I'll pull this over to my other screen so that I have it up. So for 001, we change to a 1. 010 stays a 0. 011 goes to a 1. 100 goes to a 1. 101 stays a 0. 110 goes to a 1, and all ones is a 0. So this currently is rule 90. So again, we're just applying the rule here. And I'll bring this back over and do a full screen. So I'm just putting in those rules that we had on the slide, just using an if statement. This is actually wrong. This will not work the way we want it to. And I'm gonna tell you why in a moment. But first, let's actually code up the rest of main. So I need to do more generations. I need to generate a whole bunch of these. So I'm going to say for int I equals 0, I less than however many generations you want, however many lines you want to print. So let's say 10. Let's say I want to print out 10 lines of this. Each time I'm going to apply the rules. Apply rules. Send in my array. And then after I apply the rule, I'm going to do a print line as well. So I do a print to print out that initial version. And then 10 times I'm going to apply the rules and then print the line. And this is almost done. Again, it's not quite going to be right, but it is actually almost done. So we get a pattern that sort of looks like this. The display here actually isn't very good. The zeros and ones aren't great for visualizing this. So we're going to change the print just a little bit. So inside of my loop, where I'm actually doing the printing, I'm going to say if AI, so if the current value, if that current value is a 1, then instead of printing out a number, let's just print out a 1 as a string. Here, put my brackets in. And then I'm going to say else. Let's print out. I'm just changing the way it looks here. Let's just print out a space. So if we have a 1 in our array, let's print out actually a 1. Otherwise, if we have a 0, let's just print out a space. This should look a little bit better. But the pattern, there's not really much of a pattern to it. We could increase the size. So I'm going to do that. Let's say we want 61 here. So now we got something that looks like this. It does have sort of an interesting pattern, but it's not sort of as cool as I made it sound. I mean, the whole thing's probably not as cool as I made it sound, but it's not as cool as it could be because this isn't working correctly. The reason is this. I'm updating the array, and then I'm reading from the updated array. I would call this updating in place. For any cellular automata, you never want to do this. You never want to update, and then the next iteration, read from the updated array. That's not the way you do a cellular automata. You never do it that way. So what I'm going to do to fix this is I'm going to create a new array. And I'm going to call this old array. And this is just going to be a new integer array of size array.length. So it's going to be the same size as the original one. And I'm going to actually make a copy of it. I'm going to make old array be exactly the same as new array. So we're going to do I equals 0, I less than array.length, I plus plus. And I'm going to say old array I equals array I. I'm just making a copy. That's all this does. Copy array into old array. Now, one last change to get this to work right. This needs to be changed. This is going to be old array. So that I'm always grabbing A, B, and C from the original. So we're always going to get A, B, and C from the initial array, not from the one being updated. That is a key aspect of this. If you do not do this, it will not work correctly. If I run now, we start to get maybe a little more interesting pattern. So let's increase the amount of lines we're creating. Let's do like 40 lines or something. This structure has a name. Obviously, by the edges, I obviously have stuff sort of truncated off here. So I need to make my, I need to have more lines here. So we could go up to like whatever, like 81, add 20 more lines into here or something, and you'll start to see a little bit more of it. But you can see it starts to make a structure that is symmetric and also sort of repeating. Notice this piece here. It looks the same as this piece and this one. And if we kept going, we get another one and another one. And we get more and more and more of these as we keep going. This does have a name. The structure has a name. It's called Sierpinski's triangle. It's a fractal. This will just keep generating forever. It's a fractal. So it's a simple set of rules, starting with literally just a 1 and a bunch of zeros. And that dumb set of rules, which I picked on purpose. I mean, I picked these ones on purpose, but these sort of dumb set of rules here, and just updating in the exact way I showed you on the slides. And again, you could do this by hand as well. You get a fractal. A fractal gets created if you stack up each of the generations, one on top of another. And the cool thing about this code is we can just change the rules. So let's say I want this rule to be now 0. For 1, 0, 0, I want it to be a 0. Let's see what happens. Okay. Not too interesting. Doesn't really do a whole lot. Takes the 1 from the center and sort of sends it over to the side. Right? Not too interesting. Maybe we want to take something here, turn this into a 1. Go here. Looks like it starts to print out like this. So we get another sort of triangle here where we sort of have these edges as sort of solid on the edges, but then we do have some spaces between in the center, and it sort of fills up our screen. So there's a lot of cool stuff you can do with these. There's a lot of cool things you can do with these different rules. There are other actually sort of more random fractals that actually come out of this with specific rules. So if you are interested in this sort of thing and you want to mess around with other rules, you can go look them up. You can just look up cellular automata rule 90 and it'll show you about this. And there's other rules that are cool as well. So this is sort of your basic one-dimensional cellular automata that gives you something interesting. So I know that I went over the code a little bit fast because we do have a little bit more to do, but at the very least on the VOD, you should be able to go through and take a look at this if you want a closer look at some of the code here. Hopefully that gives you a little more sort of visual stuff about arrays. Hopefully this is a little bit more interesting than coding up something to find the minimum and the maximum values in arrays, for example. So before we go to the 2D version of this, which we're not going to code up. But before we go to that, does anyone have any questions on this 1D version?
I just have one question. For the I think I missed the part when you explained it, but for the a dot length divided by 2, why'd you do that again?
So this is so I can be a bit more generic, right? So this would be 81 at the moment. So a dot length after I create a, this would be 81. Right? So I could make sure to change these two values, or I could create a value up here to say like int n equals 81, and I could throw in an n here and an n here, for instance. It's so that I get that exact center value in the array to be a 1, because they're all zeros to start with. So I say, all right, I want the halfway point, the halfway index, to be a 1. So I used a dot length because that's going to be the full length. That's going to be the 81. So in this particular case, n and a dot length are the same value. So that's why I just used a dot length there instead of creating an extra variable.
Okay, thank you.
Yep. All right, so back to here. Let's go back down to where we were at. All right, so game of life is 2 dimensions. So this adds complexity. Our neighborhood is going to be bigger. But that means more configurations, but also more useful or interesting applications. So in 1970, this is when I mentioned John Conway's Game of Life came around. The actual sort of paper on this was written by Martin Gardner in Scientific American, and it documented John Conway's Game of Life, and it described it as recreational mathematics. Maybe not something you see all the time when sort of describing mathematics, but he recommended getting out a chessboard and some checkers or something and playing for yourself. So the rules will be simple enough to play by hand, which is what I mentioned earlier. That's what John Conway did when they were figuring out what the rules should be. They were literally doing it on pieces of paper. So these days, sort of Game of Life is more of a computational cliche. Oftentimes, you sort of see it in a CS1 or a CS2 type class to sort of show you like what we're doing today, show you how sort of 2D arrays might function. But there is a lot of cool stuff to this. There was people are still studying modifications to this today. So obviously, instead of a line of cells, like what we just did with our 1D array, you have a 2-dimensional array of cells, a matrix. So we have a matrix that looks like this. Every cell can only still be 0 or 1, just like we did, but the neighborhood is bigger. That neighborhood, like I said at the beginning of the lecture today, we have this 9-cell neighborhood now. So we have the center that we pick, and we have 9 cells around it. As a quick side note, this is exactly how you do a box blur or a Gaussian blur in something like Photoshop. The neighborhood gets larger. The more blur you want, the more cells away from the center you actually involve. For Game of Life, it's only 1 cell in all directions. To make an image very blurry, it would potentially be tens or hundreds of cells away from the center that you would involve in the calculation. So then the question might be, all right, how many cells this time? With 9 total cells, 2 states each, that's 2 to the 9th power. So 512 possible configurations. Now, I don't want to code 512 rules. For the 1D version, we coded all 8. There were only 8. 2 to the 3rd power is just 8. So we just coded them all. We just had an if statement for each one. But I don't want to do this. I don't want to have 512 if statements. Each if statement has to be A, B, A, and B, and C, and D, and E, and F, and all of that. That's a lot to code up. You could do it. But I mentioned that you could play this on a chessboard and with some checkers or something, or you can do this by hand relatively easily. So we're going to define rules based on the general look of the neighborhood, not the exact configuration, just the general look. So what does that mean? That means that a cell dies. So if the center cell is a 1, and you have 4 or more alive neighbors. So I look at my neighborhood. So I take my center cell, it's a 1. I look at my 8 neighbors, and I see if there are 4 or more neighbors that are also 1s, then the center cell dies. It changes from a 1 to a 0. You can think of that in sort of a life terms as overpopulation. Or you could die of loneliness. if my center cell is alive and I look at my 8 neighbors and there's 1 or fewer alive neighbors, then you also die. Sort of again, a loneliness type situation. That takes care of a lot of possible configurations. That takes care of a whole bunch of those 512. So let's talk about the birth of a cell. If the center cell you pick is a 0, then it's going to come back to life, going to change to a 1 if it has exactly 3 live neighbors. Make sense? Sort of in between loneliness and overpopulation. Good enough. And then how does a cell stay the same? It stays alive if there's exactly 2 or 3 alive neighbors. So if it is alive, if the center cell you pick is a 1, if there are 2 or 3 live neighbors around it, then it stays alive, so it doesn't change. It stays dead if there's anything other than 3 live neighbors. So if it's already dead, there's not 3 live neighbors, it stays dead. That's it. Sort of 3 sets of rules based on sort of death, birth, and stasis. Death, birth, and stay the same. Sort of 5 conditions total: overpopulation, loneliness, stay alive, stay dead, and then birth. You can reduce this down to a set of just an if, an else if, and an else. So if you're sort of clever about it, you can reduce this down to just sort of three things that you have to look at. This has some interesting effects. So let's say, for example, there's this. So my center cell is a center I pick. So what happens in the next generation? Well, we have a center cell as alive, and we have 1 alive neighbor. I look at my neighbors, I say there's only 1 alive neighbor. So what happens? Death. In the next iteration, the next generation, this cell will die. I'm only looking at the center cell for what changes. I don't know what's going to happen to this cell because I don't know what its full neighborhood is. But this cell dies. We can look at another one. Okay, we've got a center cell being dead, and we've got 3 live neighbors. I count the neighbors in the neighborhood, so this is a birth. So this center cell will come back to life in the next generation. So that's all you do. Code-wise, it can get a little bit complicated. You'll have a bunch of for loops and stuff, but visually, conceptually, hopefully this makes sense. We just look at the center cell, look at the neighborhood, essentially count the number of neighbors that are alive, and then you determine what happens to the center cell. That's it. So for a 1D CA, the one we just saw, we stacked up the generations. We got them one on top of another, and we got, from Rule 90, we got Sierpinski's triangle. That's not going to be viable for 2D. I'm not going to take one generation and then stack it on top of another generation. That's not really going to help me visualize what's happening. So what's typical in game of life is to treat each generation like a single frame in a movie. So instead of seeing all the generations at once, like we do with the 1D, we're going to watch them over time, which makes essentially a movie or an animation. There are a few interesting structures we're going to see as this animation plays out, and I have it all written up in Java, so I'm basically going to play it for you guys in a second. Some of these structures don't change. Some oscillate back and forth. Some move across the grid. All of these have names. We might see some that I haven't listed here just because I didn't put an exhaustive list of them, but all of them have names because, again, this stuff's been studied for ever since 1970. So they all have names. For example, this is a block. And if you go through and look at every single cell here, apply the rules to every single cell and sort of draw on a new sheet of paper what the next generation would look like, you'll see that none of these change. So we have the block, we have a beehive, there's a loaf, there's a boat. You can get this sort of double boat thing as well that we might see. So these are stationary. They do not change over time. Every generation, as long as nothing comes into one of these regions. So as long as something else happening outside doesn't come into any of these white squares that sort of outline this, then these will stay the same forever. These ones oscillate between 2 states. So let me give you a quick example here of this one. So I'm going to draw it out just a little bit. I'll try to draw it out a little bit smaller than it actually is. This one oscillates. This is the easiest one. We'll see a whole bunch of these. If I take a look at, for example, this cell here, and I look at the neighborhood, it only has 1 live neighbor, so it dies in the next generation. So it's going to remain white. So this one here will die. I'll just draw it on top of this. As we go through and look at this cell, for example, it has 2 live neighbors. It's already alive, so it will stay alive. But the cells to either side of it, so this one here and this one here, they'll come back to life because they've got 3 live neighbors, both of them do. So the next generation will have a horizontal bar because this one will die as well. So between generations, as generations go on, this will flip from vertical to horizontal to vertical to horizontal and so on. So that one will oscillate between 2 states. The toad here grows out and then comes back in. The beacon will sort of have some flashing stuff in here. Blinkers are most common. Every once in a while, I see a toad from a random start, from a random initial board, but not very often. Beacons don't show up too often either. Then we have some that actually move across the grid. So gliders are quite common. I'll see if I can point one out as it gets created. They're common. They don't sort of always pop up, but they are relatively common. Lightweight spaceship, usually you have to manually create one of these because look at all the space it needs. If something else interferes and comes into this space, then the glider or the lightweight spaceship disappears. It sort of, the generations cause it to basically be destroyed. So you need all this space, and typically in a random start for a board for Game of Life, they don't stick around. There's not enough space for them to do it. So in Eclipse here, I have a version of this. This is very similar to what I have students write in CS2. Typically, the way that I do my CS2 classes is, and I don't know if other professors do this or not, but typically what I'll have is over the course of the semester, we'll have 2 or 3 larger projects that we work on together. And this typically is one of them, so that you can see how like graphics and stuff all interact with things, and classes and all that other good stuff. So here is the board for Game of Life. I have a whole bunch of squares, and the squares are just white or black. There's a bunch of blinkers. Actually, here's a beacon here. I haven't seen a beacon in a while. There's a glider moving across the screen. As soon as it interacts with there's another glider over here. And we're to a almost steady state. It's just about to go away here probably. Or not. Let's see if we get a little bit more action here. So yeah, actually beacons are something I don't usually see. I don't usually see it. So that is kind of cool. And eventually this will get to a steady state. This will get to where we only have stationary or oscillating types here. One of the reasons for that is because I'm doing the same thing here that I did with the 1D version. Notice there will never be a cell that's black on the edge. So I've sort of defined the edge as being white, and it will never change state. So you can get some sort of weirdness happening sort of in corners and stuff. Kind of like here, you would never sort of regularly see this because in the next generation, you would get a black cell here, and then this would change. But because I've set the edge to 0, you can get some weirdness at the edges sometimes. So yeah, so now we're at the steady state. So this is something, like I said, we'll code up in CS2 because it uses some graphics, obviously, and it's a little bit more complicated. But starts with a random board, and then just let it go. Just applying those sort of 3 sets of rules: the death, the birth, the stasis. And that's it. And you get some interesting stuff happening. Something that's I think you would sort of call this sort of complexity that arises out of these simple rules. We get this kind of complexity, which I think is pretty cool. So this is your simple version of Game of Life. But there's other things you can do with it as well. And playing around with it is part of the fun of messing around with these sorts of cellular automata things. So I'm gonna go ahead and cancel this. I think it's escape. Yeah, I have it set up to press escape to close it. There's more than just sort of a very sort of simple version of this. You could do a hex version. A hex version is going to have a smaller neighborhood because there's only going to be 6 neighbors rather than 9 or 6 neighbors, 7 total hexes, rather than 8 neighbors or 9 total squares. So that will change the complexity of what's happening here. That will change the rules that you have to write, and then you might come up with something kind of interesting. Other things like probabilistic rules. Maybe you only die 80% of the time for overpopulation. So maybe you allow a little bit of overpopulation to happen every generation. Maybe loneliness, maybe there's some of these cells that are okay with loneliness. So you only have a 60% chance of dying for loneliness. So you throw in some random number generation, and all of a sudden you have more complex rules, and you get more, or maybe more interesting, maybe less interesting simulation out of it. And then you go around and you tweak these, and you get them to do something a little bit different. Things like a history. Maybe if a cell has been dead for a long time, maybe it has a higher chance of coming back to life, and you modify those sort of probabilistic rules based on a history. So you keep track of a history for each cell. Maybe you keep track of the previous 10 generations of a cell. And if it's been alive a lot, maybe it'll stay dead for longer in the future, or vice versa. If it's been alive recently, maybe it has a higher chance of going back to life. So there's a lot of interesting things you can add to make this even more interesting. This idea of sort of a complex adaptive system, which is what adding a history does, actually led to things like neural networks. This idea of keeping a history of what certain cells have done led to this neural network idea. So there is sort of history as well, sort of like computer science history that's rooted in some of this too. You could have a nested setup. Maybe each cell that you saw, you could code it up so that each cell has a smaller game of life happening inside of it. That's kind of like what we are. I mean, I'm sitting here talking to you guys, but inside of me, there's a bunch of bacteria and all kinds of other stuff that's going on inside of me that is keeping me alive. So you could sort of think about the same sort of thing happening in a cell in Game of Life. Maybe there's a nested with another small game of life happening in each cell. And sort of what would that represent, or what would that look like? I don't have a slide for this on here, but I'm going to show you one more simulation. This is exactly the same style. I think over the summer I gave a colloquium on this, so I think it's on like the YouTube page or something of the computer science department, I think. This is a fluid model. It's a fluid model that's even simpler than a Game of Life I just talked about. So Game of Life, you looked at all 9 cells for a neighborhood. In this fluid simulation, you don't look at the ones on the corners. You only look at the cardinal directions. So you pick a cell and you look to the top, left, right, bottom. You don't look to the corners. A little bit more complicated about stuff that's happening in the cell. It's not just a 0 or 1. It's actually technically a 0 to 4, I think. 0 to 4. Yeah, it should be 0 to 4. So there's a little bit more stuff happening state-wise. But what you end up with, and this takes a moment to start up because I set up everything before the graphic pops up. So what you're going to see here, the graphic here is relatively small, just because of performance issues. Java's not super performant when running these. So here's the graphic. The grid is still a square, so you're still going to see some square stuff, some like the underlying grid is coming through. So what you're seeing here is this. You're seeing, think of the colors here as density. Think of it how deep the water is. So if you messed around in, say, a physics class, even in something like high school, if you messed around on a wave table before, it's usually just some sort of plastic thing, where you put a thin layer of water in, and then up from the bottom shines a light, so you can see the waves better. And you might drop some more water in, or you might sort of bump the table around and see the waves that sort of form from it. That's basically what this is. It's a top-down view. And imagine this square piece here as being high density. We just dropped some water in. We took a little dropper and we dropped a few drops at one specific location. So at this sort of corner location here. The rest of it is sort of a neutral density. We have a bunch of other sort of colors here representing that it's just a thin layer of water. So when I run this simulation, and again, it's done almost the same way as the stuff that we just did. If you look real close and squint a little bit, around the edge, it's just yellow. That's what no liquid means. So I did the same thing I did in Game of Life. I set all the edges just automatically set to 0. So nothing happens there. Just like for the 1D, just like for Game of Life. And as soon as I play this, you're going to start to see this spread out like a wave. There will be some underlying grid that you can see. You'll see it sort of start spreading out in sort of a square way. But then after some of the stuff has mixed a little bit, you'll be able to see some nice sort of curved wave action. So if I run, you start to see it sort of disperse. So the sort of wave is starting out from this high density area where we just dropped some more water in. We can still see that grid a little bit underneath, but now the waves that went up and to the right or up and to the left, they're going to bounce off. And the waves that went to the right and down, they start to create this wave front. And now we see the wave from the top and the left, they're bouncing off and they're creating this wave front here. So if I use space again. Yeah. So if I pause the simulation here, this is one of the waves. So we get this wave front action here. We have sort of a higher density. Think of it as more water in that location, which would be a wave. Same thing here. We got another one here, and we got another one here, and we're getting a little bit of constructive interference here to make it a little bit higher than the surrounding waves. And as this goes, so space again, as this goes, you'll see this wave here. It's going to bounce off the wall and sort of bounce back, and we'll get some, well, it looks like more sort of wave action in the corner. So it's sort of a sloshing sort of up in the corner and then back down. So like here, we get a little bit of sloshing here, and then the wave's going to start moving back this way. We'll get some of the sloshing here as well. So we'll see a much higher density in the corner. So it sort of sloshes up. Meanwhile, we're getting some constructive interference from the waves that are moving through each other. And so some waves will move back, and it starts to sort of level out a little bit. You know, after you wait a little while, everything sort of calms back down again. But in the meantime, so here we got some lower areas here, and we got some things bouncing. And again, it's the same thing that we just talked about. We did the 1D version. This is just a 2D version with an even simpler neighborhood than Game of Life. So like I said, I did a colloquium on this. We actually coded it up in the hour for the colloquium. I sort of went over what the rules were and sort of how you do it. And then you get this sort of top-down fluid-like simulation. This one's very simple. There are much more complicated cellular automata for fluid simulations where you can put barriers in and it actually makes like vortices and stuff. But this is the sort of the simplest version to kind of get you started on something like this. So whether we do this in CS2, I don't know. Probably not. We'll probably just do Game of Life because I have some other ones. Some of the other larger projects are like a Blackjack project and stuff like that. So typically I don't show this one for that. Let's see. So hopefully that at least is a little bit more exciting when it comes to things like arrays and 2D arrays, and maybe a little bit about how you can use them to represent different things rather than just some numbers you want to I don't know, some numbers you want to figure out which one's larger in an array or something. So that is all I have for today. OOP will be next up. PA4 is due today. I didn't put it on here, but PA5 is available right now. I think after PA5, we might take a little 1 week break. I know that we've sort of had sort of homework after homework after homework after homework, and then test and then more homeworks. So I think we'll take a short break after PA5, but that is available right now, and that will be due next week. Lab tomorrow will be a regular lab, so come for that, and then we'll sort of break you guys off into groups, and you can work on it together. Otherwise, that is all that I have. So I will see you guys tomorrow morning.
Thank you, Professor.
Yeah.